So those are the molecules that make up the paper. The electron cloud shifts a little bit, and now the molecules have an electrical polarity to them. So one side is a little more negative than the other side. And what does that mean? That means that the top surface here acts like a negative charge, and the bottom acts like a positive charge, and everything in the middle sort of cancels out. So we get this effect where the top is negative and the bottom is positive, sort of. And closeness counts. The force really drops off with distance. Closeness counts, so we get an attractive force. So even in something that is not a conductor, even if in something that's an insulator, we can get this effect. And there are some molecules that have a natural polarity to them, like which one? Water, right? Water. One side holds the electrons tighter than the other side, so there's a polarity. One side is slightly negative, the other side is slightly positive. So you can do a neat, there's actually a picture in your textbook. You can turn on the faucet real slow at home, get a stream of water. You can get a balloon, rub it up against your hair, and hold it next to the stream of water, and the water will be attracted. Doesn't matter whether the balloon is positively charged or negatively charged. Let's draw it here. What happens if it's a positively charged object next to the water stream? Bring a positively charged object up. The water molecules rotate. The positive end is repelled. The negative side is attracted. So the water molecules end up in this orientation. And where do they go? They are attracted. And the stream of water comes out over here. And if we bring up a negative charge, balloon or something, then they rotate the opposite direction, right? They rotate sort of into this orientation. They are attracted, and they come out over here. So the stream of water, it's really obvious in the stream of water the effect that the electrical charge has. They rotate, the molecules are free to rotate in the stream of water such that there's an attractive force. It doesn't matter positive charge, negative charge, you always get the attractive force. Same with all of these, right? You can't get that conductive sphere to attract to your charged object. Doesn't matter whether you bring up a positive charge or a negative charge, it's always an attractive force. You see why that is? Draw it out for, let me go back up here. If this is a positive charge like I've drawn, the negatives are attracted over, and the attractive force is closer and stronger than the repulsive force. So we get attraction. If this was a negatively charged object, what would happen? The electrons would run to the other side. The positives would be closer. That's the attractive force. The negatives are further away. That's the repulsive force. That's weaker. And so what do you end up with? An attractive force. You always get an attractive force with this induced charge separation. Always an attractive force. Okay, so we want to be able to quantify this force, right? And we use Coulomb's law. The force between two charged objects, what might it depend on? A charge on one of the objects, right? What else might it depend on? The distance. Yes. It's going to drop off, right, with distance, right? I'll write it as r. We usually use r for distance. What else might it depend on? The other charge, that's right, because you bring a charged object up next to something that's neutral, and you might not get a charge. You might not get a force. You might, right? That's what I was doing here with induced charge. You might get a force. Okay, so it's going to depend on the two charges. It's going to depend on the distance between them. It's going to drop off with the distance between them. And then to put an equal sign in here, I need a constant. K Q1 Q2 over r squared, where K is our constant. And what is it? 8.99 times 10 to the 9th. Q is the symbol we use for electrical charge. The unit is the coulomb. Capital C, coulomb. And so, of course, a force should end up in newtons. So K has the units Newton meters squared per coulomb squared. So the coulombs cancel, the meters cancel, we end up with newtons. The easiest way to use this equation, in your book they probably draw it with a vector, and you have to try to remember which direction it points. The easiest thing is just do the magnitude. Okay? Put in the magnitude of Q1, because remember, charges can be positive or negative. Does this remind you? Does this equation look familiar? Should look just like gravity, right? What was gravity look like? This is our electric force. A constant, one of the masses, another mass, and the square of the distance between them, right? Now, with mass, we only know about one kind of mass in our observable universe here, in our world that we live in. There's one type of mass, and it always attracts, it always attracts, so it's easy, right? But we know about two kinds of charge, positive and negative, and sometimes it attracts and sometimes it repels, right, depending on if they're the same sign or opposite signs. So the easiest way to do this is just to find the magnitudes. And then look at the situation and say, is this an attractive force or is it a repulsive force? If it's attractive, draw the arrows toward each other. If it's repulsive, draw the arrows away from each other. Figure out the direction that way. Okay, what else we've got here? The coulomb is a fairly large quantity compared to what we're typically measuring. So we're often seeing microcoulombs. So you might want to just review. Remember, lowercase m, milli, means 10 to the minus 3, and a mu means micro, 10 to the minus 6 coulombs. And we often write microcoulombs in most of our equations, 10 to the minus 6 coulombs. So just familiarize yourself with that unit. We see it a lot. So we're going to start out just dealing with electrical forces the same way we dealt with other forces, because that's what it's all about, right? We're just trying to make our model of the world a little more realistic. We started out back at the beginning of Physics 2a. Remember, there was no friction. Everything was a point object because we didn't know how to deal with rotation. We started with a very simple model of the world. And students always say, but this isn't realistic. But you need some tools, right? You need some fundamentals. And then we built on it. We very quickly had the ability to add in friction. And by the end of the quarter, we could add in objects that could rotate. And now we can deal with objects that have electrical charge. So it's just one more force. It's one more thing that we're dealing with, we're adding into our model so that our models are becoming more realistic. We can deal with situations that involve more variables. So on page 11 here, There's my hanging charge there. We're just interested in the one that's hanging there. What's something that might be acting on that? The weight. Down, right? What else? The other charge. Which direction? I'm going to call that F sub E, electric force. What else? Is it going down? No, it's just sitting there, right? So something must be pulling up on it. Tension in the string. That's it? I always used to say, back in previous quarter, right, 2A, I used to say, well, look and see what's touching your object. What's touching it? The string. That's our tension. And what can reach into a distance? You only knew about one thing, one force that could reach in from a distance before. That was gravity. Now we have a second one. The electric force acts at a distance, just like the gravitational force. So now we have two that can reach in from a distance. So there's our free body diagram. How about for B? Same weight acting down, is that right? What about the electric force? It's going up this time. And the tension? Also going up, right? Something like that. Oh, sorry. Got to switch. There we go. Is that better? All right. And what's next? Apply Newton's second law. So what do we say? We say the sum of the forces has to be 0 because this thing's not moving. It's in equilibrium. It's not moving, so we know the acceleration is 0. And what do we get? Tension minus Fe minus the weight has to be 0. I chose up as my positive direction. And over here I get tension plus Fe minus the weight is 0. Is that right? And so which one is bigger, the tension in case A or the tension in case B? So what do we have? We've got the tension is going to be the weight plus the electric force for A. And for B, we've got the tension is the weight minus the electric force. And the electric forces, how do they compare? Magnitudes. They're the same, right? Because the two charges are the same, the distances are the same. Where's our equation? K Q1 Q2 over R squared. Q1 and Q2 have the same magnitude in both cases. The distance is the same. K is a constant. So the force has the same magnitude in each case. The weight's the same. So the tension for A, I guess I should put a little A on those. And the tension for B are going to be slightly different. Tension for A is going to be more. Does that make sense? They're repelling each other. So the tension in A is more. In B, they're attracting each other, so that force is helping to hold up some of the weight. The tension doesn't have to hold up as much.